a band structure. Okay, and what a band structure is it's basically classifying the eigenstates of a single particle Hamiltonian. Okay, and so we go from the many-body problem to the one-body problem, which is much more manageable. Okay, and so so in band theory, which I'll say a little bit more about, basically one wants to understand the eigenstates for a single particle. Okay, and in a crystal, one can think about the Hamiltonian as a function of momentum. It's basically, I can think of the Hamiltonian as a mapping from the Brillouin zone, which is a torus, onto the Hamiltonian that has an energy gap. Okay, and so in the band theory of solids, this is a very well developed subject. One can understand the band structure of a material. Okay, and the important thing here is that this notion of the energy gap separating the ground state from the excited state happens when you have an energy gap separating the occupied electronic states from the empty electronic states. Okay, and so what we're going to seek to do is we're going to seek to understand the topological classes of these band theories. Okay, so now there are many examples of sort of topological phenomena that one can understand within the context of band theory. Okay, and so again, these are states which I can think of. So it's not that we're ignoring the interactions between electrons completely. What we are doing is we're restricting ourselves to states that can be adiabatically, where you can sort of adiabatically turn off the interactions, and the state sort of stays in the same phase. Okay, and so there are many of these. The quantum Hall effect, we'll talk about that. Topological insulators, weak topological insulators, topological crystalline insulators, and then also topological semimetals. So these are all things that we can understand within the context of band theory. And so I'm going to spend a fair amount of time talking about this. And also in later talks, the experimentalists are also going to be talking about many of these things in real materials. And so this is a subject that over the last decade there's been a huge amount of activity, and the reason for that is because the combination of having sort of these sort of rich topological type ideas, but that in combination with the fact that there are many real materials that these ideas apply to, and real experiments, and so that's what really so these ideas have really sort of come to life in the real world, which is what, as a physicist, we really would like to make happen. Okay? Now, of course, this is not the whole story about topological phases of matter. Okay? There are many fascinating topological states of matter that cannot be described within band theory. Okay? And so these are states which have what one might call an intrinsic topological order. We know that such states can exist. So the sort of classical example of this is the fractional quantum Hall effect. Okay. Now, this is also a subject which in the last, say, 5 years or so, there's been a huge amount of activity and increasing of our understanding. Okay, and so this actually, from a theoretical point of view, is actually much deeper and richer than this is. The difficulty at this point, and which I think is a challenge for our field as a whole, which I think is a big challenge that over time maybe some of you can make, give us solutions to, is how to make these richer, more exciting states come to life in the real world as well. Okay, and so at this point, the theoretical description that we have is still rather far from the original electrons. Okay, and so it's a more abstract description, and so bridging the gap between these more strongly correlated states and real materials is a tremendous challenge for physics. Now, one set of states which sort of straddles these two is topological superconductivity. Now, a superconductor really is something which is beyond band theory, in the sense that it's a correlated state of the electrons, which really is something that one can't describe by ignoring the interactions between the electrons. However, the way that we understand superconductivity, which follows from the BCS mean field theory of superconductivity, that mean field theory actually is a theory of free fermions. Okay, and so this allows one to understand superconductors in the same language of topological band theory. Okay, and so in particular, the interesting situation is if one has a topological superconductivity, and so this is an area where it's really a strongly correlated state, but we can understand them using topological band theory, and there is tantalizing recent experimental progress here at Princeton and around the world in our efforts to make topological superconductivity come to life in the real world. Okay, and so these are the sort of things that we're going to be discussing over the next 2 weeks. Now, for my lectures, I'm going to really focus on the first and the last of these. I'm going to leave it to next week for the discussion of the more richly correlated states. So my sort of introduction is going to be sort of the kinds of states that one can describe within band theory. Okay. All right. So my plan for these 3 lectures is to sort of so this morning I'm going to give the ideas of topology and band theory and introduce the sort of key conceptual tools that we have for understanding this, and then tomorrow we'll talk about topological insulators, maybe topological crystalline insulators, topological semimetals, and then on Wednesday we'll talk about topological superconductivity. Okay, so that's my plan. So I gave you some. There are many resources for you to read about this subject. Okay, so my favorite ones, of course, are the ones that I wrote. So those are the ones I gave you. But there are many more. Okay, and they're not too hard to find. Okay, so in particular, this morning's the first sort of couple lectures are going to follow reasonably closely this chapter that I wrote for this book edited by Marcel Franz and Lawrence Mollenkamp. Which I think you have a point or two to get to. Okay, so this morning what we're going to do is we're going to sort of start off, sort of talking about the sort of insulating state and how topology can use it, and then I'm going to work through some sort of very basic examples, sort of the band topology in one dimension, introducing the Su-Schrieffer-Heeger model, and so this really has a lot of the sort of key ideas built into it, okay, in the sort of simplest context, and then we'll graduate to 2 dimensions and describe the quantum Hall effect, and then if there's time at the end, we'll talk about some generalizations. Okay. All right. So let me sort of start with a puzzle here, which is so we know an insulator, what an insulator is. An insulator, we learn about an insulator when we're freshmen. We learn that an insulator insulates because the electrons are sort of bound to the atoms. They're stuck and they can't move. Okay, and really that's that fact though is a uniquely quantum mechanical fact, because it arises because the energy levels that, so the electrons are going around in their sort of circular orbits around the atoms, and when particles undergo periodic classical orbits, quantum mechanics tells you their energy levels are quantized. Okay? And so you have these quantized energy levels, and in a sort of trivial insulator, one has an energy gap separating the occupied orbitals from the empty orbitals. Okay? And so the simplest one you can imagine is just an atomic insulator where the atoms are really far apart. Then I can think of the energy as a function of momentum. It's just completely, everything's independent of momentum because every state is just localized on its own atom. So you have completely flat bands. That's the most trivial kind of insulator you can have. Now, what I'd like to contrast that with is electrons which are confined to a two-dimensional plane, but they're in a strong perpendicular magnetic field. Now, you know what electrons like to do when they're in a magnetic field? They like to go around in circles. That's what electrons do in a magnetic field. Now, that kind of motion is kind of the same motion that electrons are doing when they're going around in an atom. Okay, and so it's not so surprising that this cyclotron motion gets quantized as well. And now you might say that, well, I can't describe this within a band theory because when you have a magnetic field, then you can't talk about both the x and y components of the momentum independently because they don't commute with each other. The translations don't commute. But if you introduce a unit cell, okay, that encloses a quantum of magnetic flux, then the translations by a lattice vector in this unit cell, the x and y translations do commute. Okay, and that allows one to think of this as a band structure, which is just as good a band structure as this. Okay, and if you look at these two, so what you get is you get lambda levels here coming from this cyclotron motion, but this looks like a band structure, which is, the two look the same. Okay? If you just looked at the energy levels, you wouldn't be able to tell the difference between them. Yes?
Is there any reason to make the band structure like symmetric or square? Why can't you have a rectangle?
Oh, sure. You mean in the way I draw this unit cell?
Yeah.
Of course, yeah. So I could, the only, so I'm artificially drawing this unit cell. So it could have any, so the only constraint is that I want it to have enclose a unit of magnetic flux, so that and if I do that way, then so I think what one can show is that if I look at the commutator between the translations in one direction and the other direction, their commutator will be 0 if it encloses a quantum of magnetic flux. Yes.
And the strength of the magnetic field has to be like some rational number, right?
Well, so so here's the thing: is that what you need to have is the number of electrons that fill an integer number of these bands. Okay, so what you want is you want to have the energy gap separate the occupied states from the empty states. So you have to have exactly enough electrons to fill this band, okay? And that will happen if you have an integer number of electrons per flux quantum, okay? And that's so the ratio between the number of electrons and the number of flux quanta has to be an integer, and that's what happens in the integer quantum Hall effect. Okay, that gives you an integer number of lambda levels that are filled. So absolutely, yeah, good. Any other questions? Yes.
You're drawing circles on the top and on the bottom, but the comparison seems kind of superficial because at the bottom that circle is maybe a solution to semi-classical equation of motion, but then at the top, in a semi-classical picture, that it wouldn't move in a circle. It would just be, that's just an orbital, an atomic orbital.
No, semi-classically you have planetary orbits going around the atom. Those can go in circles, or ellipses, I guess, but yeah. They're periodic. The classical orbits are periodic, so the quantum states are quantized.
Right, but not the maybe the classical orbitals, but not even the semi-classical orbit. I mean, I don't know what that means semi-classical. There's no electric field or magnetic field. I mean, this should be a trivial equation of motion semi-classical.
Well, no, there's an electric field coming from the charges of the nuclei.
It's not changing in time. Okay, yeah. Okay.
Okay. But, okay, so the point I want to make, though, is, I mean, even if you solve these problems quantum mechanically, they look the same, okay? And the point is, though, is that they're not the same because, you know, again, thinking, you know, if I apply an electric field to this cyclotron motion problem, apply an electric field in the plane, okay, then what happens to the cyclotron orbits is that they drift perpendicular to the magnetic field, okay? So again, that's just thinking classically in terms of the classical motion of electrons. If I apply an electric field this way, then the cyclotron orbits drift, okay? And that gives rise to an electric current which flows perpendicular to the electric field. Okay? So, whereas if you did that in the trivial insulator, you wouldn't get anything, okay? And so this gives rise to the Hall effect, and in fact, miraculously, if you measure this Hall current that flows, then it defines a Hall conductivity, which is quantized in units of E squared over H. Okay, and so the question is what's the difference between these two? Okay, and that's where the idea of topology enters. So what I'm going to show you over the course of this lecture is how to understand the difference between these two as being distinguished by some kind of topological invariant. Okay. Okay. So let me just sort of talk about what a topological invariant is before attaching physics to it. Okay. So you know, I gave this example of the sphere and the donut. Pardon me.
Can I ask you a question about the previous?
Sure. Oh, before this?
Can you explain again why the lambda levels? Can you explain again why we can't have these lambda levels? So you said that they should be either fully occupied or completely empty.
Yeah. So if the lambda level is partially filled, okay, then at least in this picture where we're ignoring the interactions between electrons, then the ground state will not be separated by an energy gap from the non-ground state. So you have some ground state where you fill some of the states of the lambda level. So there are going to be lots of other degenerate states that are degenerate with that, where I just fill them in a different way. Okay? So it won't be whereas what we're interested in talking about at this point is states where the ground state is separated by an energy gap from all the other states. Okay, so that's what breaks down. Now, you point to an interesting problem. Okay, and this has been a problem that you know we've learned a lot about over the last several decades, which is when you have electron-electron interactions, then that degeneracy of the partially filled lambda level can be lifted in very interesting ways. Okay, and that gives rise to the fractional quantum Hall effect, which you know I think you know you're going to learn about next week. So yeah. Yes.
So in the top picture, I mean, the way that I can understand insulator is that electrons are bound to the nucleus, right? So they cannot move freely. That's what the system called insulator. But then what happened for this Hall states?
Well, yeah, it's different, isn't it? Because it's, you know, if you apply an electric field, then it moves, so it's not really bound. But still, you have a situation where you have an energy gap separating the occupied states from the empty states.
Yeah, from the energy point of view, I can understand.
Yeah, so they're different. So they are different, and what we want to do is we want to understand that difference on the basis of thinking about this electronic structure. That's what we want to do. Yeah.
So you're just saying that the energy spectrum of the Hamiltonians are identical and they equally have the same eigenspaces, right? That's